Good evening, everybody. It's Thursday, April 23rd, and this is Nighttime Mathematics Radio. The show works the same way it always does. You tweet your questions into @NightMathRadio on Twitter, and I'll try to answer them live here on the air. So we got some questions already come in from Twitter, but to give people a little bit longer to tweet in, we'll wait about a minute or two, then we'll get right to it. This is Nighttime Mathematics Radio. Back after this. Welcome back, everybody. This is Nighttime Mathematics Radio. Well, we had one interesting tweet tonight asking questions about surfaces of resolution. These are volumes of revolution. These are objects you make by taking a normal one-dimensional function and then rotating them about some line. And by doing so, you create a three-dimensional object. Let's take a look. Now, two questions got asked like this, and for both questions, they're kind of nice for once. This is a nice thing to do. They said, set these up, but don't necessarily do the integrals. So nothing you're asking is to actually do the integrals. It's just saying, what would the integral be? How do you do, what would the integral look like? And for both questions, we have exactly the same function. The function looks like this. The function is defined from y equals 1 to y equals 6. And you take the region bounded by those, by x equals 0, so by the y-axis. So if here are our axes, we're looking at something, this thing's bound by y equals 1, y equals 6, way up here, the y-axis itself, and then a function x is equal to y times e to the minus 1/2 y. Properly speaking, it said 0.5, but I've got a notepad, so I'll type 1/2. What does that area look like? It comes out, has some maximum in here, and begins to ease back in again. So we're interested in this region right here. And so the first question we're asked about is, well, what about the solid form when you take this region? We call this region R, just to give it a name. Revolve R around x equals minus 1. What's back here? That's this line. So what we're doing is we're taking this region here and then swinging it around y equals -1. Oops, not there. The bottom part doesn't count. Around y equals -1. So it's sort of a hollow cylinder in the middle. And then we have the mirror image of that shape here. So it goes out to a maximum, eases back in. Oops. Eases back in a little further out, sorry. Eases back in like that. So we have that same shape over here. We want to know the volume of this whole thing. Well, how do we do that? Well, this thing's actually asking for a variation on the method of disks. Remember, the way the method of disks works is you say, for method of disks, if you swing a function around an object, you say, well, what I would see, imagine we didn't have this restriction in the middle. Then we could say, well, okay, everything's filled in, so I just take a disk out to this radius. So my radius is equal to, my outside radius is just, well, it's 1 more than the x value, so it's 1 plus y e to the -1/2 y. Right, because you got this distance 1 between x equals -1 and the axis itself. And so the overall radius to this outside bit is that. It's 1 plus radius. But there's also an inside radius, which is always 1. Because there is no object in here. We're bounding the region by the y-axis. So that's what makes this hollow cylinder in the middle. So instead of disks, we have things that look like washers. And so this gets called the method of washers. Where if you think about what the slice looks like here, you have a circular slice with an inner radius of 1 and an outer radius of 1 plus y equals to the -1/2 y, like that. And so what's the area of that washer? So the area of the washer at height y is pi r outer squared minus pi r inner squared. So in this case, that's, well, we have to square this thing. So it's pi 1 plus y e to the -1/2 y quantity squared minus pi times 1 squared. So we have to do this out by FOIL. We have pi plus 2 pi y e to the -1/2 y plus the second bit squared plus y squared e to the, well, what is e to the -1/2 y squared? It's, when you square this, this gets doubled, so it becomes e to the -y. Right? Because e to the -1/2 y times e to the -1/2 y is e to the 1y. Minus pi. So the pi pieces cancel. And there's our washer area. It's 2 pi y e to the -1/2 y plus y squared e to the -y. Okay, so what's the volume of the washer? Well, we imagine this thing has some relatively initially, if you're thinking about limiting it out, before you take the limit, it would have some finite volume, some finite thickness, delta y, and then the limit, this thing will have a differential bit of volume, which is equal to 2 pi y e to the -1/2 y plus y squared e to the -y times dy. Because you imagine this dy is what in the limit replaces your delta y. This is your little infinitesimal bit of thickness. So how do we find the overall volume? And the answer is, well, we just integrate our dv's. We integrate this, 2 pi y e to the -1/2 y plus y squared e to the -y dy, evaluated from 1, where the region starts, up to 6. And now that looks a really hard integral to do, so at this point we take refuge in the fact they said set up and do not evaluate the integral, and we're done. And that's part A. How about part B? Well, in part B, it's exactly the same region. We don't have a new region to think about here. This is the same region we had before. So So nothing's new there. It's just that we're rotating it about a different line. Before we were rotating around x equals -1. Now we're rotating it around y equals 8. Let's see what that looks like. So now with the same region we had before, right, going from 1 up to 6, looks like out and eases back in. There's our region. Except this time we're rotating it around a line up here. We're rotating it around y equals 8. So now what are we going to do? Well, remember the thing we know is this length here. That's the easy thing to work in terms of. So what happens if we rotate that around this line? The answer is instead of getting a disk like we had before, we get a cylinder. For every y value, you get a cylinder as you wrap this thing around. And this thing looks upside down up here. Oops. There's the upside down region. You have big cylinders. So the thing looks like a big donut with sort of an interesting internal shape. So the question here is, instead of asking what is the area of what's the volume of that disk, we need to ask what's the volume of this cylindrical shell, because this time we're doing method of shells. And the answer is, well, the area of a cylindrical shell is 2 pi r times the height. Well, what's the height? The height is just y. So in this case, the area of a shell from height y is equal to 2 pi times the radius of the shell, which is now, well, what is it? It's at 6 it's 2, at 1 it's 7. So what is this thing? And the answer is it's 8 minus y. Because after all, that's how far away you are from 8. Right? The question is, how far are you from the center of rotation? The answer is 8 minus y. Times the height. The height is literally our function. It's our y. It's our x. It's our x length, which is y e to the minus 1/2 y. And so our differential bit of volume is just that times a little differentiable bit of thickness. So our dV here is a of y dy, because that dy is in the limit our little differential bit of thickness. So that's 2 pi times 8 minus y times y e to the minus 1/2 y. Times dy. You notice the units work out here. We hope. We have a distance here. We have a distance here. And we have a distance here. And distance times distance times distance is volume. So again, we just need to integrate this across all possible y values. So the integral from 1 to 6 of 2 pi 8 minus y e to the minus 1/2 y dy is our volume. Again, notice the difference here is that the easy way to characterize this is this way around. So you might ask, well, why didn't we do this with disks again? After all, we could figure out how big each disk is. The answer is because that would be hard. Because we would now have to figure out what this distance is, which means we'd have to solve this thing for x, and that's going to be really difficult. It's much easier to use the functional form we've been given, which is in terms of y. And finally, we have one last problem that isn't a method of shells or anything, but that will require, unfortunately, will require doing an integral. If it had to catch us eventually. And that's the problem. It says find the average value of f of x is equal to 140x minus 70, sorry, plus 70 over x squared plus x plus 5 quantity squared on minus 1 comma 1. So what is that asking us to do? Well, remember, the way you find the average value of a function over an interval is you integrate the function over that interval and then divide by the length of the interval. And that gives us the average height of the function. It's exactly what you would do for an average if you think about it taken to the limit. If you had two numbers that would take an average, you'd add them up and then you'd add up your two numbers and then divide by 2. If you had 3, you'd add your 3 numbers and divide by 3. So here we're saying, well, if we imagine that we have our functional form and we have 2 possible values, we could do that. 3, 4. How do we do this? Let's see. We have to integrate. So our interval length is 2, so we need half the interval from minus 1 to 1 of 140 plus 70x. Oops, 140x plus 70. It's important. The other one would be much harder to do, actually. Over x squared plus x plus 5 quantity squared dx. Now, if we're having a really bad day, we'd start squaring. But let's not have a very bad day. If we're not having a bad day, we think, I wish there's a substitution I could do to make this easy. Because down here I've got a x squared plus x plus 5. And if this was just 1 over x squared, 1 over u squared, that would be so nice. Well, let's see if we can do it. A good way to see if a u substitution will work is start. If it doesn't work, try again. Let u equals x squared plus x plus 5. Then du is equal to 2x plus 1 dx. Well, I don't have a 2x plus 1, but I've got the next best thing. I've got 140x plus 70, which if I factor 70 out is a 2x plus 1. So I'll factor 70 out of this thing. That gives me 35 times the integral from minus 1 to 1 of 2x plus 1 over x squared plus x plus 5 squared dx. Now, doing our substitution, this gives us the integral of 35 times the integral. I'm going to figure out the limits in a minute. This thing on top is just my du over u squared. Now I have to figure out the limits. And there's 2 possibilities here. One is that we do this integral, then back substitute and plug 1 and minus 1 in again. The other possibility is we just see what happens when you plug minus 1 and 1 in here. If I plug minus 1 in, I get u for minus 1 is minus 1 squared, which is 1. Minus 1 is 0, plus 5 is 5. If I plug 1 in, I get 1 plus 1 is 2, plus 5 is 7. So this is the integral from u equals 5 to u equals 7. Yes. Of du over u squared. Is this always safe? Let's see. 35. What's the integral of 1 over u squared? Well, it's minus 1 over u evaluated from 5 to 7. Right? Because derivative of u to the minus 1 is minus u to the minus 2 for 1 over u squared. So that's 35 times. And you notice that this is minus, but that's good because this is now decreasing in this order. So this is minus 1/7 plus 1/5. Well, that's 35 times. Might as well reverse it to put the positive 1 first. You can see that we want the common denominator to be 35, 7 times 5. So that's 7 35ths minus 5 35ths. So that's 35, times 2 35ths, which is just 2. So the average value of that function over the interval is 2. If you ever doubt yourself with this sort of thing, it's worth doing a sanity check. You know, is 2 at least plausible? If you have a grapher nearby, you can do that. Let's switch to our grapher for a second, which still has some point set from another week. That's okay. So I pull out my grapher here, get rid of this point set, and let's just plot y is equal to that function, 140 plus 70x over, and that's not quite what I want, so I'll put the over first, 140x plus 70, divided by x squared plus x plus 5 quantity squared. Let's scroll. Remember, we want this between -1 and 1, so let's look between -1 and 1. Need to zoom out a little bit. As you see here, let's see, at 1 it's up to around 4 or 5. At -1 it's down here at -2.5. So 2 is a pretty plausible halfway between, and that's what we see. And that is in fact the average. The average would be right here. Okay, this is Nighttime Mathematics Radio. I hope that helped the person who asked this question. Let's take one more break to see if anybody else asks any more questions. If so, I'll answer those too. If not, we'll end the show. This is Nighttime Mathematics Radio. Well, Twitter's looking pretty quiet, so I think it's time to end the show. So in this weird world where the classes have all stopped, but the homework just keeps going on and on and on, keep tweeting your questions to @NightMathRadio. I'll try to help you out weeknights, 9 p.m. Pacific time. Can't do it every weeknight, but I'll do it most of them. So everybody keep doing the homework. Stay safe out there. Good night, everybody.